To, in some sense, paint a broad picture of some of the challenges that we face while trying to model OPVs using numerical ab initio methods. And so the first such challenge that I've identified is that the fact that electrons are moving around, of course. Now there's this quantity called the short circuit current that we need to be able to compute in order to predict power conversion efficiencies, and this quantity here can be expressed as the product between the number of incident photons and this so-called external quantum efficiency here, in which we've placed all of the complicated processes that occur inside the device. Now, of course, we're talking here about transport properties, exciton generation, dissociation, and so on and so forth. And so we expect it to be, well, we know it is quite complicated to model. So the first thing we can look at is experimental values. What does it actually look like? And we see that indeed it is a complicated function of the frequency, and it depends on a lot of factors, including, of course, what's the actual material that we're looking at. And so the first thing we can do to order zero, let's say, is to take sort of the average value of the most efficient one and just take it as a simple step function that we truncate at the band gap energy. And so if we do that, we compute the band gap with DFT, and we compare with experiment, and unsurprisingly, we see not such a good correspondence. What we do notice, however, is that some of the most efficient ones are in pretty good agreement with this 65% coarse approximation. And so it's not impossible that some of these points could be brought up here on that curve given some structural or device optimization of some sort. Of course, in order to confirm or infirm this hypothesis, we need to be looking at these processes more closely. Which brings me to my second challenge. Electrons are not alone. They spend most of their time surrounded by this hole, orbiting around this hole, which is in and of itself a very difficult thing to describe. But also there's phonons, ions, defects, and all sorts of things that are very hard to model in a theoretical type of way. And so I've divided this challenge in two sub-challenges, if I can say, one of which is there are ions. Here is a graph that we produced showing that there's a good correspondence between what we call the kinoid character, which is a measure of the average CC bond length inside the polymer backbone, and the band gap of the resulting polymer. Now that's very interesting because first it actually shows that the problem is not only an electronic one, but in a big way a structural one. And also it allows us to be able to predict some of the important values that we need to model these things in a very efficient way without having to go through the whole electronic structure computation, which can get quite heavy in some of these systems. And so that's quite encouraging. And now the second sub-challenge is that there are more electrons. Now we've discussed this a few times so far. Ian and Michel mentioned it already. This binding energy of excitons inside the organic materials. Here there's a cartoon showing some excitonic-like quasi-particle inside silicon when compared to inside an organic crystal. And we see that indeed in silicon, and that's partly what makes silicon such a good candidate for PVs, is that it's very delocalized. And so the binding energy is very weak, and it can be very easily described taking very simple approximations like the effective mass things. And so it's very easy to model. In the case of organics, however, we can't take such simple approximations. We need to go through very heavy type of ab initio methods, like solving the Bethe-Salpeter equation and so on and so forth. And so when you want to screen a lot of candidates, it becomes very limiting very fast. And so that's an issue. And which brings me to my third challenge, is that in order to dissociate these excitons, as we all know, we need interfaces, and in terms of electronic structure calculation, interfaces are probably one of the biggest challenges. Here's an example of a study that's been done on such interfaces in molecular dynamics. And it's quite a nice study because they show some of the annealing properties when we add temperature in the whole process and so on, but there's no information on electronic structure. And when we talk about charge transfer states and dissociating the excitons and so on, we need information about these electronic structure of these type of things here. So, and that we absolutely can do. Now, I guess the last challenge that I've identified is, and it's a shared problem, I guess, is that the best OPV is not a needle, but really hay in the haystack. In a sense, there's so many possibilities that it becomes really hard to filter all these. Now, from a theoretical standpoint, of course, we want to filter a lot of candidates. We need to go through high throughput calculations if we really want accurate electronic structure answers. However, if we can somehow model in more simple way, like what was done in the kinoid versus aromatic parameter, then we could get answers much faster. Also, with high throughput calculations, we get a lot of data. What we do with this, should we hop on the big data bandwagon and try to find these correlations? That's a big question. And of course, collaboration are crucial. Like Michel showed, we can get really strong insights on what's going on in these things when theory meets experiment. And so with this, I'll thank you for your attention.
Merci Vincent. Any questions? Okay, I'll ask. Jean-Michel, are you going to ask a question or are you coming for your talk? Okay.
So you are modeling the exciton and some properties. Would it be, don't you think it would be interesting to model traps? I mean, we have plenty of defects in organic semiconductors, and try to figure out, by chemistry, what can be a couple of defects like double bonds, triple bonds, I don't know, or kinks or whatever, and try to model the impact of these defects on the local, polarization, which will attract charge or repel them. Will you do that?
Absolutely, it would be really interesting to be able to do so. However, modeling traps is, what we have access to is a simple unit cell. If I want to add a trap in, say, a 100-unit cell, like a defect or something like that, then I need 100 times the number of atoms, and I can't simulate that.
I'm not sure.
Well, there are
a couple of things that you would need. You would need first the band gap of the local species that you create. Mm-hmm. If it is acceptor or donor, and then if it has polarizability,
there are ways by which you can compute defects. What I've seen in the literature is not ab initio. It usually goes through the use of tight binding approaches, for instance, or there are also these so-called order n method in DFT that you can use to compute larger systems. However, they do come with their own problems, like the convergence studies are not as convincing and things like that. If you want really to go with the ab initio type approach, then it really becomes problematic.